Welcome to Milky Narratives. Tonight, leave behind the noise of the waking world, relax your mind, and drift with me into the quietest mysteries of the universe. 1. Reality feels solid, but it may be an illusion. What if everything you can touch, see, and experience is hiding a deeper reality that your brain was never designed to perceive? Right now, as you sit here listening to these words, everything around you feels solid. The chair beneath you feels solid. The floor beneath your feet feels solid. The walls around you feel solid. Even your own body feels solid. It feels obvious, certain, undeniable. After all, you've spent your entire life interacting with a world that appears stable and real. You can touch things, hold things, measure things. If you drop your phone, it falls. If you walk into a wall, the wall wins. Reality seems straightforward, reliable, predictable. And yet, what if almost everything your senses tell you about the universe is wrong? Not slightly wrong, not partially wrong, but fundamentally wrong. What if the reality you experience every day is merely a simplified model, a carefully edited version of existence? A survival interface created by your brain. Because tonight, we begin a journey toward one of the most unsettling discoveries in modern science. The universe you experience may not be the universe that actually exists. And the deeper scientists have looked into reality, the stranger that possibility has become. Imagine for a moment that you were born inside a submarine. You have never seen the ocean directly. You have never stepped outside. Everything you know about the world comes from screens mounted on the walls. One screen shows temperature, another shows depth, another shows nearby objects detected by sonar. Over time, you become very familiar with these displays. You trust them completely. You navigate your entire life through them. But then one day, someone tells you something astonishing. The screens are not the ocean. They are merely representations of the ocean. Simplified translations, useful approximations, helpful illusions. And suddenly you realize that the world you've been experiencing is only a tiny, filtered glimpse of something far larger. According to many neuroscientists and physicists, this may be exactly how your brain interacts with reality. Your senses do not show you the universe itself. They show you a version of it. A highly compressed simulation designed for survival. Because evolution never optimized your brain to perceive objective truth, it optimized your brain to stay alive. Those are not necessarily the same thing. Imagine one of your distant ancestors wandering through a prehistoric forest hundreds of thousands of years ago. A rustling noise comes from the bushes. Something moves. The ancestor who immediately assumes it is a dangerous predator survives. The ancestor who pauses to carefully analyze every detail of objective reality may not. Natural selection rewards usefulness, not perfect accuracy. Over millions of years, our brains evolved to detect patterns, threats, opportunities, and resources. Not the deepest nature of existence, not quantum mechanics, not space-time curvature, not the underlying structure of reality. Simply survival. As a result, what you experience every day may be less like reality itself and more like a user interface. Consider your smartphone. When you tap an icon, you see a small, colorful image. Perhaps a camera icon, perhaps a music app, perhaps a folder. But the icon is not what actually exists inside the phone. Beneath that simple image lies an incomprehensibly complex world of electrical signals, transistors, binary code, memory systems, and mathematical operations. The interface hides the complexity, and that is precisely why it is useful. Now imagine that your entire perception of reality functions in a similar way. The colors you see, the sounds you hear, the sensation of solidity, the feeling of time flowing forward. These experiences may be icons, useful shortcuts, efficient representations, not necessarily the deepest truth. This idea sounds almost philosophical, but modern science has repeatedly forced us to confront uncomfortable examples. Take color, for instance. Look around the room. Perhaps you see white walls, blue clothing, green plants, a red object sitting nearby. The colors appear real. They seem to exist independently in the world. Yet physics tells a different story. Color does not actually exist outside your mind. The universe contains electromagnetic radiation, different wavelengths of light. But nowhere in those wavelengths is there anything called red. There is no redness floating through space, no blueness embedded inside photons. Your brain creates color. It translates certain wavelengths into subjective experiences. In other words, one of the most vivid aspects of your daily reality is a construction generated inside your skull. And color is only the beginning. Sound offers another example. When a tree falls in a forest, it creates vibrations in the air. Tiny fluctuations in pressure move outward in waves. Yet the sound itself does not exist until a brain interprets those vibrations. The roar of thunder, the melody of music, the voice of a loved one. These experiences emerge within consciousness. They are not properties floating independently through space. Reality, as you experience it, is already more subjective than most people realize. And the deeper scientists have explored, the more surprising the situation becomes. Because it isn't just color, or sound, or taste. The very concept of solidity may be an illusion. The chair beneath you feels dense. The floor beneath your feet feels firm. Your body feels substantial. Yet when physicists examine matter at the atomic level, something astonishing appears. Atoms are mostly empty space. In fact, if an atom were enlarged to the size of a massive sports stadium, the nucleus would be smaller than a pea sitting at the center. Everything else would be emptiness, vast emptiness. The atoms inside your body, the atoms inside your house, the atoms inside mountains, oceans, and planets, all are overwhelmingly empty. So why does reality feel solid? Why don't your hands pass directly through objects? The answer lies not in physical contact, but in invisible forces. Electromagnetic interactions prevent atoms from passing through one another. What you experience as touch is actually fields interacting, a dance of forces occurring between particles. You have never truly touched anything in the way you imagine. Not once, for your entire life. And if that realization feels strange, it is only the beginning. Because as we continue our journey, we will discover that particles sometimes exist in multiple states at once. That observation may influence reality itself. That space and time may not be fundamental, and that the universe beneath everyday experience may be stranger than anything human beings ever imagined. The world feels solid, stable, obvious. Yet science keeps uncovering clues that reality is hiding something deeper, something vast, something profoundly unexpected. And tonight, we are only beginning to pull back the curtain. 2. Your brain never sees the real universe. Right now, your mind may be constructing a version of reality that is dramatically different from what actually exists. If everything we experience is a kind of interface, then a disturbing question immediately follows. What exactly is hiding behind it? Because once you begin pulling apart the illusion of solidity, something strange happens. The world starts looking less like reality itself, and more like a carefully edited presentation. A translation. A simplified story your brain tells itself every moment of your life. And the deeper scientists investigate perception, the more astonishing that story becomes. Imagine for a moment that an alien civilization arrived on Earth tomorrow. Their technology is vastly more advanced than ours. Their senses evolved under completely different conditions. They perceive forms of energy that humans cannot detect. They see dimensions of reality we never knew existed. Now imagine standing beside one of these aliens while both of you look at the exact same tree. You see green leaves, brown bark, branches moving gently in the wind. The alien sees something entirely different. It sees magnetic fields flowing through the trunk, electrical signals moving between cells, infrared radiation radiating from every leaf. Perhaps it even perceives patterns hidden within space itself. Which one of you is seeing the real tree? The uncomfortable answer may be neither. Both observers are simply experiencing different translations of the same underlying reality. This idea sits at the heart of one of the most profound mysteries in science. Your brain does not directly experience the external world. It never has, not for a single second. Everything you have ever seen, everything you have ever heard, everything you have ever tasted, smelled, touched, loved, feared, or remembered has existed inside your mind. That statement sounds almost philosophical, but neurologically speaking, it is completely true. Right now, light is entering your eyes. Tiny packets of electromagnetic radiation called photons are striking specialized cells at the back of your retina. Those cells convert the incoming information into electrical signals. The signals travel through your optic nerve. They reach various regions of the brain. Neural circuits begin processing patterns, edges, movement, color, depth, contrast. And somewhere within that vast storm of electrical activity, your conscious experience appears. The remarkable thing is that at no point does your brain ever leave the darkness of your skull. It never directly touches the outside world. It never encounters trees, or stars, or oceans, or faces. It only receives signals, tiny streams of information. And from those signals, it constructs an entire universe. Think about that for a moment. Everything you call reality is built from interpretation. Your brain is not passively observing the world. It is actively generating your experience of it. In a sense, you are not seeing reality. You are seeing your brain's best guess about reality. And sometimes that guess is spectacularly wrong. Consider optical illusions. You have probably seen them before. Images where two lines appear different lengths despite being identical. Shapes that seem to move despite remaining perfectly still. Colors that appear to change depending on their surroundings. These illusions reveal something important. Your brain is not showing you reality exactly as it is. It is showing you what it expects to see. Much of perception involves prediction. The brain constantly makes assumptions. It fills gaps, corrects errors, constructs patterns. Most of the time, this process works beautifully. It allows you to navigate the world efficiently. But illusions expose the machinery behind the curtain. They reveal that perception is not a window, it is a model. In fact, modern neuroscience increasingly suggests that perception functions more like controlled hallucination than direct observation. That phrase sounds shocking at first, yet many researchers argue that what we experience is a carefully constrained simulation generated by the brain. The external world provides incoming data. The brain combines that data with expectations. The result becomes conscious experience. Reality, as you know it, emerges from that interaction. Imagine watching a movie through a damaged projector. The projector receives information from the film reel, but it also contributes its own distortions. Dust, blur, color shifts, artifacts. The final image becomes a combination of both. Likewise, your experience of the universe may be a mixture of external reality and internal interpretation. This realization becomes even stranger when we consider how little of the universe humans can actually detect. The visible spectrum, the colors you see every day, represents only a tiny fraction of the electromagnetic spectrum. Beyond red lies infrared radiation. Beyond violet lies ultraviolet. Then X-rays, gamma rays, radio waves, microwaves. An enormous range of phenomena surrounds you constantly. Yet your eyes remain blind to almost all of it. Imagine listening to a symphony while hearing only a single instrument. That is roughly what human perception does. Most of reality never enters awareness. And vision is only one example. Your ears detect a limited range of frequencies. Dogs hear sounds you cannot. Bats navigate through echolocation. Sharks sense electrical fields. Birds may perceive Earth's magnetic field. Other species inhabit sensory worlds radically different from our own. Each experiences a unique version of reality, which raises an extraordinary possibility. What if humans are not seeing the universe as it truly is? What if we are merely experiencing one narrow slice of an incomprehensibly larger picture? The more science advances, the more plausible that idea appears. Consider dark matter. Astronomers estimate that ordinary matter, the matter making up stars, planets, oceans, and human beings, accounts for only about 5% of the universe. Everything you have ever touched belongs to that tiny fraction. The remaining 95% appears to consist of dark matter and dark energy, mysterious components we cannot directly observe. Think about that. Most of the universe is invisible. Not metaphorically invisible, literally invisible. Human senses cannot perceive it. Even our most advanced instruments detect it only indirectly. Gravity reveals its presence. Cosmic expansion reveals its influence, but its true nature remains unknown. In a very real sense, humanity may be living inside a universe largely hidden from view. And perhaps the strangest part of all is that this hidden reality may extend far beyond dark matter. Quantum physics suggests that beneath everyday experience lies a world that behaves nothing like common sense. Particles act like waves. Probabilities replace certainties. Events occur that seem impossible from the perspective of ordinary intuition. The reality your brain evolved to navigate is not the reality quantum physics describes, and that may not be a coincidence. After all, evolution never needed us to understand the quantum world. It only needed us to survive long enough to reproduce. The result is a brain exquisitely adapted for hunting, gathering, socializing, and avoiding danger, not for understanding the deepest structure of existence. Perhaps that is why modern physics often feels so unintuitive. The universe beneath the surface may simply be far stranger than the environment that shaped our minds. And as we continue our journey deeper into reality, we will discover that the illusion runs even further than perception. Because the objects around you, the walls, the mountains, the stars, even your own body, may be far emptier than they appear. And hidden within that emptiness lies one of the most astonishing discoveries science has ever made. A discovery that forces us to ask whether solid reality exists at all. 3. The world is mostly empty space. If every atom inside your body lost its empty space, the entire human race could fit inside a sugar cube. Take a slow breath for a moment. Look around the room. Notice the walls, the furniture, your hands, your feet. Everything appears solid, dense, substantial, real. After all, that is exactly what your senses have been telling you since the day you were born. You can sit on a chair, lean against a wall, pick up a book, hold a glass of water. The world feels packed with matter, packed with substance, packed with physical stuff. But tonight, we are about to uncover one of the most astonishing facts in all of science. A fact so strange that it sounds almost impossible the first time you hear it. Almost everything around you is empty. Not partially empty, not mostly empty, almost entirely empty. And that includes you. In fact, if every atom inside every human being on Earth suddenly lost all of its empty space, the entire human race could fit inside a single sugar cube. Not a building, not a city, not a mountain. A sugar cube, the kind that disappears into a cup of coffee. At first glance, that sounds absurd. Surely there must be some mistake. After all, billions of people occupy enormous amounts of space. Cities stretch across continents. Humanity has covered the planet with roads, houses, skyscrapers, and infrastructure. How could all of that possibly fit into something so tiny? The answer begins with understanding what an atom actually is. Back in school, atoms are often shown as tiny solar systems. A nucleus sits in the center. Electrons orbit around it. The image is simple, convenient, easy to remember, but it hides an astonishing truth. The nucleus itself is incredibly small compared to the overall size of the atom. Imagine enlarging a single atom until it becomes the size of a giant football stadium. The atom now stretches hundreds of feet across. You might expect the nucleus to fill much of the field. Instead, it would be smaller than a marble sitting at midfield. Everything else? Almost entirely empty space. The electrons would exist far away from the center, occupying regions that make the atom seem enormous compared to its nucleus. But between them lies vast emptiness, an atomic wilderness, a microscopic desert. And because every object around you is built from atoms, that emptiness exists everywhere. Inside your body, inside mountains, inside oceans, inside entire planets. Matter is not what it appears to be. The solid world we experience every day is largely an illusion created by forces operating within that emptiness. Imagine removing all the empty space from a single atom. The atom would collapse dramatically. Now imagine doing that for every atom in your body. You would shrink to a size smaller than a grain of dust. Yet your mass would remain exactly the same. Every kilogram, every molecule, every particle still present, just compressed into an unimaginably tiny volume. And this raises a deeply unsettling question. If atoms are mostly empty space, why doesn't your hand pass through a table? Why don't you fall through the floor? Why does reality feel solid at all? The answer turns out to be one of the greatest tricks nature has ever played. Because despite what your senses tell you, you have never truly touched anything. Not once. Think about that. Every object you've ever held, every handshake, every hug, every raindrop, every grain of sand, you never physically touched any of them in the way you imagine. Instead, what you experience as touch is the interaction of electromagnetic forces. The electrons in your skin repel the electrons in other objects. As your hand approaches a table, invisible force fields push against one another. The atoms never actually merge, the nuclei never collide. What you interpret as physical contact is really the sensation of electromagnetic resistance. Your entire experience of solidity emerges from invisible interactions occurring inside mostly empty space. Reality begins feeling less like a collection of objects and more like a dance of forces, a giant cosmic choreography performed by particles and fields. And the deeper physicists investigated this strange atomic world, the stranger it became, because the atom itself was only the first layer. Inside the nucleus, scientists discovered protons and neutrons. Then they discovered those particles were not fundamental either. Inside them lurked quarks. Even deeper, modern physics describes reality through quantum fields that stretch across the entire universe. In this picture, particles are not tiny solid balls. They are excitations, ripples, localized disturbances in underlying fields. Imagine standing beside a calm lake. A wave appears on the surface. The wave seems like an object, something separate, something distinct. But the wave is not actually independent from the lake. It is simply the lake doing something. According to quantum field theory, particles may be similar. Electrons are not little spheres flying through space. They may be temporary ripples within a universal electron field. Quarks are ripples, photons are ripples. Even the atoms inside your body are collections of organized disturbances moving through invisible fields. The deeper we look, the less reality resembles the solid world of everyday experience. And yet it becomes even stranger, because emptiness itself may not truly be empty. For centuries, scientists imagined a vacuum as absolute nothingness, a perfect void, a place where absolutely nothing exists. But modern quantum physics tells a very different story. Even in the emptiest regions of space, activity never fully stops. Particles appear and disappear. Quantum fluctuations flicker in and out of existence. Energy bubbles beneath the surface. The vacuum itself seems alive, restless, active, dynamic. In a sense, what we call empty space may be one of the busiest places in the universe. And suddenly the phrase nothing becomes surprisingly difficult to define, because if empty space contains fields and fluctuations and potential energy, is it really empty at all? The universe appears to be hiding layers beneath layers. Every time science thinks it has reached bedrock, another deeper level emerges. The solid world becomes atoms. Atoms become particles. Particles become fields. Fields emerge from mathematics we are still trying to understand. And somewhere beneath all of it lies a reality that may be far stranger than anything our ancestors could have imagined. Perhaps stranger than anything our brains evolved to comprehend. Yet this journey is only beginning. Because once physicists discovered that matter is mostly empty space, they encountered an even more shocking problem. At the smallest scales of existence, particles themselves refuse to behave like ordinary objects. They can appear in multiple possibilities. They can exist as probabilities rather than certainties. And in some experiments, they seem to challenge the very idea of objective reality. The closer we look, the less the universe resembles a machine, and the more it resembles a mystery. If you're still awake, leave a comment telling me which fact about reality feels hardest to believe. And as we continue our journey, prepare yourself for one of the strangest discoveries in all of science, because the particles that make up reality may not be where you think they are, until someone looks. 4. Quantum particles refuse to behave normally. At the smallest scales of existence, nature seems to ignore the rules that govern everyday life. By now, the universe has already stolen away several things we once thought were certain. First, we learned that the world our senses experience may be little more than a carefully constructed interpretation. Then we discovered that solid matter is mostly empty space. The chair beneath you, the walls around you, even your own body, all built from atoms that are almost entirely empty. That realization alone feels strange enough. But tonight we are about to cross an even stranger boundary. Because once scientists looked deeper than atoms, deeper than nuclei, deeper than the particles themselves, reality stopped behaving normally. In fact, it began behaving so strangely that even the physicists who discovered it spent decades arguing about what it actually meant. Imagine throwing a baseball. You know exactly how it behaves. It travels through the air. It follows a predictable path. At any given moment, the ball occupies one specific location. Even if you close your eyes, you assume the ball continues moving along that path. That assumption feels obvious, almost self-evident. After all, it reflects how reality works in everyday life. Objects have positions, events have causes. The future follows from the present. Simple, predictable, comforting. Now imagine throwing a baseball and discovering that it somehow traveled through two different paths at the same time. Imagine discovering that the ball did not decide where it was until someone looked at it. Imagine finding out that the ball behaved like a wave spread across space, rather than a physical object. At that point, you would probably assume your experiment was broken. Yet this is exactly what happens in the quantum world, and scientists have confirmed it again and again for more than a century. The deeper we look into nature, the less it resembles common sense. The story begins in the early 20th century. Physicists believed they were close to understanding everything. Isaac Newton's laws explained motion. Maxwell's equations explained electromagnetism. Astronomy was progressing rapidly. Many researchers felt that physics was nearly complete. Only a few small details remained unresolved. Then, nature pulled the rug out from under everyone. One of those details involved light. For centuries, scientists debated whether light was a wave or a particle. Experiments seemed to support both answers. Sometimes, light behaved like a wave moving through space. Other times, it behaved like a stream of individual particles. The contradiction made little sense. How could something be both? Then things became even stranger. Scientists began studying electrons, tiny particles that make up atoms. Surely electrons would behave like ordinary objects. After all, they were particles, little pieces of matter. But the experiments revealed something astonishing. Electrons behaved like waves too, not occasionally, not under special circumstances, consistently. The more carefully researchers looked, the more impossible the results became. And nowhere was this more shocking than in one of the most famous experiments in scientific history, the double-slit experiment. At first glance, the setup appears incredibly simple. A beam of particles is fired toward a barrier containing two narrow openings. Behind the barrier sits a detector screen. If particles behave like tiny bullets, they should pass through one slit or the other. Two openings should create two impact regions. Straightforward, predictable, exactly what common sense expects. But that is not what happens. Instead, scientists observe an interference pattern, a pattern normally associated with waves. The particles somehow behave as though they pass through both slits simultaneously. They interfere with themselves. They spread out like ripples on water. And somehow they create a pattern that should be impossible for ordinary particles. At first, researchers assumed multiple particles were interacting with one another. Perhaps they were influencing each other along the way. So they performed the experiment again, this time firing particles one at a time. One electron, then another, each traveling completely alone. Surely now the wave pattern would disappear. Yet it didn't. The interference pattern slowly emerged anyway, as though each individual electron somehow knew about both slits, as though each particle explored multiple possibilities simultaneously. It was one of the most astonishing discoveries in scientific history. And it gets even stranger. Scientists then decided to watch the particles. They placed detectors near the slits to determine which opening each electron actually passed through, a reasonable thing to do. After all, if something is going through two slits, we should be able to observe it. But the moment they measured the path, the interference pattern vanished. Completely. Suddenly the particles behaved like ordinary particles again, one slit or the other, never both. It was as though the act of observation changed reality itself. The universe seemed to notice it was being watched. Now, to be clear, physicists do not literally mean that human eyes possess magical powers. Observation in quantum mechanics means interaction, measurement, the exchange of information. Yet the mystery remains. Why does reality behave differently when measured? What exactly is happening before measurement occurs? Even today, there is no universal agreement. Different interpretations of quantum mechanics offer different answers. Some physicists argue that particles exist in multiple possible states simultaneously. Others suggest hidden variables remain undiscovered. Still others propose that every quantum event creates branching realities, entire parallel universes splitting apart continuously. The fact that respected scientists seriously debate these possibilities should tell you something profound. We still do not fully understand what quantum mechanics is telling us about reality, and this uncertainty extends far beyond laboratory experiments. The quantum world is not separate from our universe. It is the foundation of it. Every atom in your body obeys quantum laws. Every star, every planet, every molecule. Everything emerges from this strange underlying framework. Yet somehow the bizarre behavior becomes hidden at larger scales. The world of everyday experience appears stable, solid, predictable, like calm waves disguising the storm beneath the surface. Imagine standing on a frozen lake. The ice appears perfectly still, safe, motionless. Yet beneath the surface, billions upon billions of water molecules move chaotically. Their activity remains hidden from view. Likewise, everyday reality may conceal an incredibly strange quantum ocean underneath. An ocean where certainty becomes probability, where particles behave like waves, where possibilities exist before outcomes, where nature follows rules unlike anything our ancestors could have imagined. And perhaps the most astonishing part is this: quantum mechanics is not some fringe theory. It is the most successful scientific framework ever created. Its predictions have been tested countless times. Modern computers, lasers, medical scanners, smartphones. Virtually every advanced technology in your life depends on quantum physics being correct. The equations work beautifully, consistently. Yet despite its extraordinary success, we still struggle to explain what it means. The mathematics tells us what happens, but the deeper question remains unanswered. What is reality actually doing beneath the equations? As our journey continues, we will discover that the mystery becomes even more unsettling. Because some experiments suggest that quantum particles may not merely behave strangely. They may force us to question one of the oldest assumptions humanity has ever made: the assumption that reality exists in a definite state before we observe it. And if that assumption turns out to be wrong, the implications are far stranger than almost anyone realizes. 5. The strange experiment that changed physics forever. A single beam of light revealed something so bizarre that scientists are still arguing about its meaning today. Imagine spending your entire life believing you understand how reality works. Objects exist, events happen, causes produce effects. The universe follows clear rules. Then one day you perform an experiment so simple that it could fit on a laboratory table. And suddenly, everything you thought you knew begins to fall apart. Not gradually, not after decades of debate. Immediately. This is exactly what happened during one of the most famous experiments in the history of science, An experiment so strange that more than a century later, physicists are still arguing about what it actually means. And the most remarkable part, it begins with something incredibly ordinary: a beam of light. At first, that hardly sounds revolutionary. After all, light surrounds us constantly. Sunlight fills the sky, lamps illuminate our homes, stars shine across the universe. Light feels familiar, comforting, predictable. Yet hidden inside that familiarity lies one of the deepest mysteries ever discovered. To understand why, we need to briefly step back into the scientific world of the 19th century. At the time, most physicists believed light was a wave. The evidence seemed overwhelming. Wave behavior explained reflection, refraction, interference, diffraction. The mathematics worked beautifully. As far as science was concerned, the question appeared settled. Light was a wave. Case closed. But nature had other plans. When researchers began performing increasingly precise experiments, strange cracks started appearing in the story. One of the most famous involved the double-slit experiment, a setup so simple that its consequences remain almost unbelievable. Imagine a barrier containing two narrow openings. Behind it sits a screen. A beam of light shines toward the slits. If light behaves like tiny particles, common sense predicts a straightforward result. Some particles pass through the left slit, others pass through the right. Two bright bands appear on the screen. Simple, predictable, exactly what everyday intuition expects. But that is not what happens. Instead, a complex interference pattern appears. Bright regions alternate with dark regions. The pattern resembles overlapping waves on a pond. It is precisely what scientists would expect if light were behaving like a wave spreading through both slits simultaneously. For a while, this seemed to confirm the wave theory. Mystery solved. Except it wasn't. Because then, physicists asked a seemingly innocent question. What happens if we reduce the light until only a single photon travels through the apparatus at a time? Surely now, the wave pattern should disappear. After all, one photon cannot interfere with other photons if no others are present. And yet something extraordinary happened. The interference pattern remained. Slowly, photon by photon, each individual particle arrived at the screen as a tiny point. But after enough arrivals, the familiar wave pattern emerged. It was as though each photon somehow interfered with itself, as though it explored both paths simultaneously before deciding where to appear. The implications were astonishing. Imagine throwing a single pebble into a pond and watching it somehow create interference with itself. Imagine firing a single bullet and discovering it traveled through two doorways at once. That is roughly how bizarre the results seemed. Even today, the experiment feels almost impossible to visualize. Yet countless repetitions have confirmed the same outcome, again and again and again. Nature appears to behave this way, whether we like it or not. But then came the twist that changed physics forever. Scientists decided to determine which slit each photon actually passed through. A reasonable question. If something travels through two paths, surely we should be able to observe the process directly. So detectors were placed near the openings. The experiment was repeated, and suddenly the interference pattern vanished. Completely. The moment information became available about the photon's path, the wave-like behavior disappeared. The photons now acted like ordinary particles, one slit or the other, never both. It was as though reality changed its behavior when observed. And this is where the story begins to feel almost surreal, because the photons themselves had not changed. The apparatus remained nearly identical. Only one thing was different. Information existed about what happened. The universe seemed to care whether the path could be known, not whether a human physically looked. Not whether someone took notes, but whether information about the event became available at all. For many physicists, this was the moment reality became profoundly mysterious. Because what exactly was occurring before observation? What was the photon doing? Where was it? How could it simultaneously behave like a wave and a particle? No one knew. And remarkably, no one still knows with certainty today. The equations of quantum mechanics predict the results perfectly. They are among the most accurate predictions ever made in science. Yet the deeper meaning remains controversial. Richard Feynman, one of the greatest physicists of the 20th century, famously suggested that the double-slit experiment contains the central mystery of quantum mechanics, the puzzle from which all other quantum strangeness emerges. Because once you understand the implications, everyday notions of reality begin to unravel. Some physicists interpret the experiment through the Copenhagen interpretation. According to this view, quantum systems exist as probabilities until measurement occurs. Reality remains fundamentally uncertain until interaction forces a specific outcome. Others dislike this explanation. They argue that probabilities alone cannot tell the whole story. Alternative interpretations have emerged over the decades. One of the most famous is the many worlds interpretation. According to this idea, the photon does not choose a single path. Instead, reality itself branches. Every possible outcome occurs, each within its own parallel universe. In one branch, the photon travels through the left slit, in another, through the right. In countless others, different quantum possibilities unfold. The universe continuously splits into multiple versions of itself. The concept sounds like science fiction, yet it arises directly from attempts to explain experimental results, and some respected physicists take it very seriously. Other researchers propose hidden variables, unknown mechanisms operating beneath quantum theory. Still others suggest entirely new frameworks waiting to be discovered. The remarkable fact is not that physicists disagree. The remarkable fact is that nature forces them to ask such extraordinary questions in the first place. Because before quantum mechanics, reality seemed straightforward. Objects existed independently. Events unfolded predictably. The universe felt objective, stable, certain. The double-slit experiment shattered that confidence. It revealed a layer of reality where certainty gives way to possibility, where observation becomes deeply significant, where particles behave like waves, where intuition repeatedly fails. And perhaps most unsettling of all, where the universe appears less like a machine and more like something fundamentally mysterious. The deeper scientists looked, the more reality resembled a collection of probabilities waiting to become actual events. Imagine standing before a vast ocean hidden by fog. You cannot see the waves clearly. You can only estimate where they might be. Then suddenly the fog parts, revealing a single outcome. Quantum mechanics often feels similar. Before measurement, possibilities exist. After measurement, one reality emerges. But what exactly happens in between? That question remains one of the greatest unsolved mysteries in science. And the story becomes even stranger, because future experiments would suggest that the mystery is not limited to photons, or electrons, or laboratory equipment. It may extend to the very concept of observation itself. As we continue our journey, we will encounter a possibility so unsettling that even Einstein struggled to accept it. A possibility suggesting that reality may not fully settle into existence until it is observed. And if that idea contains even a grain of truth, the implications reach far beyond physics. They reach directly into the nature of existence itself. 6. Why particles can exist in multiple places at once. Before you look at them, quantum particles may be exploring many possible realities simultaneously. By now, reality has become a very strange place. The solid world around us turned out to be mostly empty space. The atoms inside our bodies became clouds of probability. Light behaved like both a wave and a particle. And one of the most famous experiments in scientific history suggested that the universe somehow behaves differently when information becomes available. For centuries, humanity imagined reality as a giant machine, a cosmic clock. Every object had a definite position. Every event had a clear cause. The future unfolded from the present like gears turning inside an enormous mechanism. Then quantum mechanics arrived, and suddenly the gears disappeared. Tonight, we take another step into that mystery, because according to the mathematics that governs the quantum world, a particle may not occupy a single location before it is measured. Instead, it may exist in a strange state known as a superposition, a state where multiple possibilities coexist simultaneously. At first, that sounds impossible. After all, everyday life doesn't work that way. Imagine looking at your car in the driveway. You don't assume the car is simultaneously parked in 5 different cities. You don't imagine your coffee cup existing both on your desk and inside your refrigerator. Objects occupy places. That seems obvious. Yet nature appears to play by very different rules at the smallest scales. To understand why, imagine standing at the entrance of a vast maze. There are thousands of possible paths leading toward the exit. If you were walking through it, you would choose one route at a time. Left, right, straight ahead, step by step. But quantum particles seem to behave differently. The mathematics suggests they explore all possible paths simultaneously, not because they possess intelligence, not because they make decisions, but because their existence is fundamentally described by probabilities rather than certainties. This idea sits at the heart of quantum mechanics. Before measurement occurs, a particle is represented by something called a wave function. The wave function does not describe a single definite reality. Instead, it describes a collection of possible realities, a landscape of probabilities, a map of what might happen. Only when measurement occurs does one specific outcome emerge, and this is where our intuition begins to break down, because the language itself can be misleading. When physicists say a particle exists in multiple places at once, they do not necessarily mean it behaves like a tiny marble physically occupying several locations. The reality is subtler, and perhaps even stranger. The particle exists in a state that cannot be fully described using ordinary concepts like here or there. Instead, it occupies a realm of possibilities, a cloud of potential outcomes, a mathematical description that resists everyday language. This may sound abstract, so let's consider an analogy. Imagine listening to an orchestra before the conductor signals the first note. The music has not yet begun, yet countless possible melodies exist within the instruments. Different notes, different combinations, different futures waiting to unfold. Once the performance begins, one sequence emerges. One specific arrangement becomes reality. Quantum systems behave in a somewhat similar way. Before measurement, many possibilities exist. After measurement, one outcome appears. Of course, every analogy eventually breaks down. Because quantum mechanics is not merely unfamiliar, it may be fundamentally unlike anything human beings evolved to experience. Our brains were shaped by survival on the African savanna, not by navigating subatomic probability clouds. And that evolutionary limitation may explain why quantum physics feels so deeply counterintuitive. Nature was never obligated to make sense to us. Nature was only obligated to exist. In fact, some of the greatest scientists in history struggled with these ideas. Albert Einstein famously disliked aspects of quantum mechanics, not because the mathematics failed. The mathematics worked beautifully. What troubled him was the apparent randomness, the lack of certainty, the suggestion that reality itself might be fundamentally probabilistic. Einstein believed there must be a deeper layer, some hidden mechanism not yet discovered, something restoring order beneath the chaos. His famous remark captured this discomfort perfectly. God does not play dice. Yet experiment after experiment continued supporting quantum theory. The universe seemed remarkably comfortable playing dice. And nowhere was this more evident than in a phenomenon known as quantum tunneling. Imagine rolling a ball toward a hill. If the ball lacks sufficient energy, it cannot reach the other side. That is how ordinary objects behave. The laws of classical physics are clear. No energy, no crossing. Simple. But quantum particles sometimes do something astonishing. They appear on the other side anyway, not because they climbed over the barrier, not because they smashed through it, but because the wave-like nature of their existence allows a probability of appearing beyond it. In effect, particles occasionally pass through obstacles that should be impossible to cross. This sounds absurd, yet quantum tunneling is not theoretical speculation. It happens constantly throughout the universe. Without it, the sun would not shine. The nuclear fusion reactions powering our star depend upon quantum tunneling. The sunlight warming Earth, the energy feeding ecosystems. The very existence of life as we know it relies upon particles behaving in ways that seem impossible. Reality is not merely strange at the quantum level. Its strangeness makes our existence possible, and the mysteries do not end there. As physicists continued exploring quantum systems, they encountered a deeper question. If particles exist as probabilities before measurement, what exactly causes those probabilities to become reality? When does possibility transform into actuality? What determines the outcome? For decades, scientists have debated these questions. Some interpretations suggest that measurement causes the wave function to collapse. The cloud of possibilities narrows into a single reality. Others argue that collapse never truly occurs. Instead, all possibilities continue existing in parallel branches of reality. Every outcome happens, every path unfolds. The universe continually divides into countless versions of itself. Still, others propose that our understanding remains incomplete, that some deeper theory waits beyond quantum mechanics, a hidden layer beneath the probabilities, a framework we have yet to uncover. The truth is that no consensus exists. The equations predict observations with extraordinary accuracy, yet their deeper meaning remains one of the greatest mysteries in science. And perhaps that uncertainty tells us something important. For centuries, humanity assumed reality was something obvious, something directly accessible, something that could be described using common sense. Quantum mechanics shattered that assumption. The closer we look, the more reality resembles a vast landscape of possibilities. A world where certainty emerges from uncertainty, where particles behave like waves, where outcomes exist as probabilities before becoming facts, and where the foundations of existence appear far stranger than anyone imagined. Yet an even more unsettling question still awaits us. Because if particles can exist in multiple possibilities before measurement, what role does observation actually play? Does reality become definite only when information is created? Does observation reveal reality, or does it help create it? Those questions have haunted physics for more than a century. And as we continue our journey deeper into the foundations of existence, we will encounter one of the most controversial possibilities ever proposed, a possibility suggesting that what we call reality may not be fully formed until it is observed. If true, the implications reach far beyond laboratories and equations. They touch the very nature of existence itself, and they force us to ask a question that sounds more like philosophy than science. What if observation is not merely something that happens within reality? What if it is part of what brings reality into being? 7. Does observation create reality? Some interpretations of quantum mechanics suggest that reality may not fully exist until it is observed. Imagine waking up tomorrow morning and discovering something extraordinary. Not that aliens exist, not that faster than light travel is possible, not even that we live inside a simulation. Something stranger, something far more unsettling. Imagine discovering that reality itself remains unfinished until it is observed, that the universe does not fully decide what it is doing until information about it exists. At first, this sounds absurd. Reality should exist whether anyone is watching or not. The moon should remain in the sky when nobody looks at it. A tree should continue standing in the forest whether or not anyone is nearby. Mountains do not disappear when hikers leave. Galaxies do not vanish when telescopes turn away. These assumptions feel so obvious that questioning them almost seems ridiculous. And yet, deep within quantum mechanics, physicists encountered results that forced them to ask whether reality might be more complicated than common sense suggests. To be clear from the beginning, modern physics does not claim that human consciousness magically creates the universe. The popular version of that idea often spreads across the internet. Videos claim that reality appears because humans observe it. Books suggest that thoughts alone shape the physical world. Scientists generally reject such simplistic interpretations. But the actual mystery is no less fascinating, because quantum mechanics does raise a profound question. What role does observation play in determining physical reality? And remarkably, more than 100 years after the birth of quantum theory, no one fully agrees on the answer. The story begins with a problem known as wave function collapse. As we discussed earlier, quantum particles are described by wave functions. These wave functions contain multiple possible outcomes, multiple potential realities. Before measurement, the particle exists as a cloud of probabilities. After measurement, one specific outcome appears. The mystery lies in the transition. How does possibility become reality? When exactly does the change occur? What causes it? Imagine flipping a coin. Before it lands, you do not know whether it will show heads or tails. But the coin itself already possesses a definite state. You simply lack information. Quantum systems appear different. Before measurement, the uncertainty may not merely exist in your knowledge, it may exist within reality itself. Nature may genuinely not have decided. And if that sounds strange, even the pioneers of quantum physics struggled with it. Niels Bohr argued that quantum properties become meaningful only through measurement. Werner Heisenberg developed uncertainty principles that fundamentally limited what could be known. Erwin Schrödinger, meanwhile, became so uncomfortable with some implications that he invented one of the most famous thought experiments in history. A cat, a box, and a question that still haunts physics today. Now, before anyone worries, no actual cat was harmed. Schrödinger designed the scenario specifically to demonstrate how bizarre quantum mechanics seemed. Imagine a sealed box. Inside sits a cat. Also inside is a tiny radioactive atom. If the atom decays, it triggers a mechanism releasing poison. If the atom does not decay, the cat survives. Quantum mechanics tells us that before observation, the atom exists in a superposition of possibilities. It has both decayed and not decayed, at least mathematically. But what about the cat? Does that mean the cat is simultaneously alive and dead? Common sense screams no. Reality cannot work that way, yet the equations seem to allow exactly that conclusion. Schrödinger intended this as a criticism, a demonstration of how absurd quantum mechanics appeared when extended into everyday life. Ironically, the experiment became one of the most famous illustrations of quantum theory ever created, because it highlights a profound tension. Where exactly does the quantum world end and ordinary reality begin? At what point does uncertainty transform into certainty? No one knows, and the deeper scientists explored, the stranger the situation became. In the 1970s, physicist John Wheeler proposed a series of thought experiments that pushed the mystery even further. One of these became known as the delayed choice experiment. The implications remain astonishing. Imagine a photon traveling through an experimental apparatus. Normally, we would assume its behavior is determined by conditions present when it begins its journey. Cause comes before effect. Past comes before future. That seems obvious. Yet Wheeler's experiment suggested something remarkable. The decision about how to measure the photon can be made after the photon has already entered the apparatus, and somehow the results still match the chosen measurement. It almost appears as though the photon's earlier behavior depends upon information determined later. Now, physicists are careful here. The experiment does not literally prove that the future changes the past, but it does challenge our intuitive understanding of time and causality. Reality once again refuses to behave according to common sense. The more closely we examine quantum systems, the harder it becomes to imagine particles carrying definite properties before measurement occurs. Instead, some interpretations suggest that reality remains fundamentally open until interaction creates a specific outcome. This leads directly to one of the most famous statements ever made about quantum physics, a remark attributed to Wheeler himself. No phenomenon is a phenomenon until it is an observed phenomenon. Even today, physicists debate exactly what those words mean. Some embrace the Copenhagen interpretation. Others prefer many worlds. Still others explore objective collapse theories or hidden variable models. Each attempts to answer the same question. What is observation actually doing? And surprisingly, modern experiments continue deepening the mystery. One particularly fascinating phenomenon is quantum entanglement. Einstein famously called it spooky action at a distance. When two particles become entangled, their properties become linked. Measure one particle, and information about the other becomes instantly determined, even if they are separated by enormous distances. At first glance, this seems impossible. Nothing should travel faster than light. Yet experiments repeatedly confirm the predictions. The universe appears to possess connections that defy our ordinary picture of reality. And perhaps that is the deeper lesson emerging from quantum mechanics. Not that consciousness creates reality, not that minds magically control matter, but that reality itself may be far stranger than the classical worldview ever imagined. The universe may not consist of tiny objects carrying fixed properties through space and time. Instead, it may be built from relationships, interactions, information, possibilities becoming actual events. The solid world of everyday experience emerges from something deeper, something less intuitive, something we are only beginning to understand. Think back to our ancestors staring into the night sky thousands of years ago. The stars appeared fixed, perfect, permanent. The earth seemed motionless beneath their feet. Everything felt obvious. Then science revealed a deeper reality. Earth moved around the sun. The stars were distant suns. Galaxies filled the cosmos. Each discovery forced humanity to abandon comfortable assumptions. Quantum mechanics may represent another step in that journey, a reminder that reality is not obligated to match human intuition. The universe has no reason to conform to common sense. After all, common sense evolved to help primates survive on a small planet, not to understand the deepest foundations of existence. And perhaps the greatest surprise is that the mystery continues. Because if observation does not merely reveal reality, if information itself plays a fundamental role, then another profound question emerges. What exactly is information? Is matter truly the foundation of existence, or could something even deeper lie beneath it? As our journey continues, we will descend into one of the most radical ideas in modern physics, an idea suggesting that information, not matter, may be the true building block of reality. And if that possibility is correct, everything we think of as physical may be emerging from something far more abstract than anyone ever imagined. If you're enjoying this journey into the deepest layers of reality, consider subscribing for more cosmic mysteries. And as we continue deeper into the hidden architecture of existence, prepare yourself for a possibility that sounds almost impossible. The universe may be made of information before it is made of matter. 8. Entanglement, the universe's invisible connection. Two particles can remain mysteriously connected across enormous distances, as if space itself doesn't matter. Imagine waking up tomorrow morning and discovering that two dice exist somewhere in the universe. One sits on your kitchen table, the other rests on a distant planet orbiting a star thousands of light years away. You roll your die. The moment it lands on a 6, the distant die instantly lands on a 1. You roll again. A 3 appears. Instantly, the other die becomes a 4. No signals travel between them. No wires connect them. No hidden messenger carries information across space. Yet somehow, they remain perfectly linked. At first glance, this sounds impossible. It sounds like science fiction, or perhaps magic. After all, one of the most fundamental principles in physics is that information cannot travel faster than light. According to Einstein's theory of relativity, light is the ultimate speed limit of the cosmos. Nothing should communicate instantaneously across vast distances. Nothing should ignore space itself. And yet, deep within the quantum world, nature appears to do something astonishingly close to exactly that. Welcome to one of the strangest discoveries ever made, quantum entanglement, a phenomenon so bizarre that even Albert Einstein refused to believe it represented the true nature of reality. And yet, experiment after experiment continues to confirm that entanglement is real, not as a theoretical curiosity, not as mathematical speculation, but as an actual feature of our universe. To understand why this shocked physicists so deeply, we first need to understand what entanglement actually means. Imagine two quantum particles interacting, perhaps two photons, perhaps two electrons. Under certain conditions, those particles become linked, not physically connected, not joined by some invisible string. Instead, their properties become correlated in a way that makes them behave like parts of a single system. From that moment onward, describing one particle separately becomes impossible. You must describe both together, even if they later move far apart. Very far apart. Imagine taking one particle and leaving it on Earth, then placing the other aboard a spacecraft traveling across the galaxy. Years pass. The distance between them grows to billions of kilometers, perhaps even light years. Yet according to quantum mechanics, their connection remains. The system still behaves as a unified whole. This alone sounds strange, but the truly shocking part emerges when measurements occur. Suppose the particles possess a property called spin. Without getting lost in technical details, think of spin as a quantum characteristic that can be measured in different ways. Before measurement, neither particle possesses a definite spin value. Instead, both exist within a shared quantum state, a cloud of possibilities. Then a scientist measures one particle. Instantly, the system produces a result, and remarkably, the second particle's measurement becomes correlated as well. No matter how far apart they are, no matter how much space lies between them. At first, physicists suspected a simple explanation. Perhaps the particles carried hidden instructions all along. Maybe they secretly knew what answers to give before they separated. That would preserve common sense. Reality would remain local, orderly, predictable. Einstein strongly preferred this possibility. After all, the alternative seemed absurd. How could two particles influence one another instantly across vast distances? Einstein famously referred to entanglement as spooky action at a distance. The phrase was not intended as praise. It reflected his discomfort, his suspicion that quantum mechanics must be incomplete. Surely some deeper explanation existed, some hidden layer of reality, some missing piece that would restore order. For decades, physicists debated the issue. And then, in 1964, a physicist named John Bell proposed something extraordinary. Bell realized that the disagreement was not merely philosophical. It could be tested. His work produced what became known as Bell's theorem, a mathematical framework capable of distinguishing between hidden variable theories and genuine quantum entanglement. For the first time, nature itself could decide. The experiments began, and the results were astonishing. Again and again, quantum mechanics won. Bell's inequalities were violated. The particles behaved exactly as quantum theory predicted. The hidden variable explanations struggled. The universe seemed to reject common sense. And with every new experiment, the evidence grew stronger. Throughout the late 20th century and into the 21st, increasingly sophisticated tests confirmed the same conclusion. Entanglement was real, not because physicists wanted it to be, but because nature insisted upon it. The universe appeared fundamentally interconnected in ways nobody expected. Now it is important to clarify something. Entanglement does not allow faster-than-light communication. You cannot use entangled particles to send messages instantly across the galaxy. Relativity remains safe. The cosmic speed limit survives. Yet despite this, entanglement reveals something profound. The universe cannot always be understood as a collection of separate, independent objects, at least at the quantum level. Sometimes reality behaves as though distance itself becomes secondary, as though separated particles remain aspects of a larger whole. And that realization carries enormous philosophical implications. For centuries, humans viewed reality as a machine, a giant assembly of individual components, separate objects interacting through space. But entanglement suggests that separation may not always be fundamental. Beneath the surface of reality, deeper relationships may exist, connections invisible to our everyday experience, connections woven directly into the fabric of existence. Imagine looking at a tapestry from extremely close range. You see individual threads, red threads, blue threads, golden threads. Each appears separate, independent. But step back, suddenly a larger image emerges. The threads were never truly isolated. They were always parts of a greater pattern. Some physicists wonder whether entanglement hints at something similar. Perhaps the apparent separation we experience is not the deepest level of reality. Perhaps space itself emerges from underlying relationships. Perhaps what we perceive as distance is not as fundamental as it appears. These ideas remain speculative, yet they are being taken increasingly seriously within modern theoretical physics, especially in attempts to unite quantum mechanics with gravity. Because surprisingly, entanglement keeps appearing wherever researchers search for the foundations of reality. Some theories even suggest that space-time itself may emerge from vast networks of quantum entanglement. In this picture, space is not the stage upon which physics unfolds. Space becomes a consequence of deeper quantum connections. The universe starts looking less like a collection of objects moving through space, and more like an immense web of relationships generating space itself. If true, the implications are staggering. The distances separating stars, galaxies, clusters of galaxies, even the enormous voids spanning billions of light years, all may emerge from something more fundamental, something hidden beneath the geometry of the cosmos. And perhaps this is why quantum mechanics continues to feel so mysterious. The theory does not merely challenge our understanding of particles, it challenges our understanding of reality itself. Every time we think we have reached the foundation, another layer appears beneath it. Matter becomes atoms. Atoms become particles. Particles become quantum fields. Fields become information, and information becomes relationships. The deeper we descend, the less the universe resembles a collection of things, and the more it resembles a network of connections. Yet an even stranger mystery awaits us. Because if entanglement hints that reality is built from information and relationships rather than objects, then we must confront a startling possibility. What if space itself is not fundamental? What if the three-dimensional world surrounding you right now is emerging from something deeper, something more abstract, something that exists beneath the very fabric of the cosmos? And that possibility leads us directly toward one of the most radical ideas in modern physics. The idea that reality itself may be built from information. 9. The speed limit of reality. Nothing can travel faster than light, but quantum physics may be hiding loopholes stranger than science fiction. Imagine standing on Earth and flipping a flashlight toward the moon. The beam races across space at nearly 300,000 kilometers per second. In just over a second, the light arrives. Fast, incredibly fast. Faster than anything humans have ever built. Yet even at that extraordinary speed, the journey is not instantaneous. Information still takes time to travel. The universe enforces a speed limit, a cosmic law, a rule so fundamental that modern physics is built upon it. Nothing can travel faster than light. Not a spaceship, not a signal, not a particle, not even information itself. At least, that is what Einstein's theory of relativity tells us. And for more than a century, every experiment has supported that conclusion. The speed of light appears woven directly into the fabric of reality. It is not merely a technological limitation. It is a structural feature of the universe itself. But as we have discovered repeatedly throughout our journey, nature rarely behaves exactly as we expect. And once quantum mechanics entered the picture, physicists encountered phenomena that seemed to dance dangerously close to violating this cosmic speed limit. Not quite breaking it, but certainly challenging our intuition. To understand why this matters, imagine a universe with no speed limit at all. Suppose information could travel instantly. The consequences would be extraordinary. The sun could vanish and Earth would know immediately. A message could be sent across the galaxy with no delay. Cause and effect would begin behaving strangely. In some situations, events could appear to happen before their causes. The orderly structure of space-time described by relativity would begin to unravel. Einstein realized this early. The speed of light was not simply a number. It protected causality itself. It preserved the distinction between past and future. Without it, reality might become chaotic. Yet quantum entanglement seemed to hint at something uncomfortable. As we saw in the previous chapter, entangled particles remain mysteriously connected. Measure one particle, the outcome of the other becomes correlated, even across enormous distances. At first glance, this sounds like information traveling instantly. And if that were true, relativity would be in serious trouble. Einstein certainly thought so. This was one reason he found quantum mechanics deeply unsettling. The idea of spooky action at a distance appeared to violate everything relativity stood for. But experiments gradually revealed something subtle, something strange, and something surprisingly elegant. Entanglement creates correlations. Yet those correlations cannot be used to transmit usable information faster than light. Imagine two people receiving identical sealed envelopes. Neither knows what is inside. When one person opens their envelope and finds a red card, they instantly know the other envelope contains a blue card. No signal traveled between them. No information was transmitted at that moment. The relationship already existed. Quantum entanglement works somewhat similarly. The particles share a deeper connection established before measurement occurs. The moment one particle is measured, the correlations become apparent. Yet no controllable message can be sent through the process. Relativity survives, at least for now. But quantum physics was not finished challenging our assumptions, because another strange feature emerged from the mathematics, one that continues to fascinate physicists today: quantum tunneling. Earlier, we briefly mentioned that particles sometimes appear on the opposite side of barriers they should not be able to cross. The phenomenon sounds impossible. Imagine throwing a tennis ball at a brick wall. Common sense tells you what happens. The ball bounces back. It certainly does not appear on the other side. Yet quantum particles occasionally behave differently. They possess a small probability of appearing beyond obstacles that classical physics forbids them from crossing. This effect is not science fiction. It happens constantly throughout nature. Inside stars, inside atoms, inside the electronic devices surrounding you. Without quantum tunneling, the sun would stop shining. The chemistry supporting life would cease. Reality itself would look very different. And while tunneling does not allow faster-than-light travel, it reminds us that quantum reality often finds pathways unavailable to ordinary objects. Nature seems to possess loopholes, not violations of physical law, but exceptions to common sense. The deeper we investigate, the more reality resembles something far stranger than a mechanical universe. Then there are hypothetical particles, objects that have never been observed but continue to appear in theoretical discussions. Among the most famous are tachyons, particles that, if they existed, would always move faster than light. Unlike ordinary matter, which requires infinite energy to reach light speed, tachyons would begin beyond the speed limit. They could never slow down below it. The idea sounds fascinating, yet it comes with severe problems. Tachyons would create paradoxes, messages arriving before they were sent, effects preceding causes, time itself becoming tangled. For this reason, most physicists suspect tachyons do not exist. No evidence has ever been found. Still, the fact that such possibilities emerge from mathematical exploration reveals how deeply the speed limit shapes reality. Light speed is not merely fast. It acts as a boundary, separating what the universe permits from what it forbids. And yet, perhaps the strangest possibility lies not in particles moving through space, but in space itself. Because Einstein's theory contains an extraordinary loophole. While nothing can move through space faster than light, space-time itself can expand. And remarkably, it already does. The universe is growing. Galaxies are drifting apart. The fabric of space stretches continuously. In some regions, distant galaxies recede from us faster than light. At first, this sounds impossible. But they are not moving through space faster than light. Space itself is expanding between us. Imagine drawing two dots on the surface of a balloon. As the balloon inflates, the dots move apart. Neither dot is crawling across the rubber. The surface itself stretches. Likewise, galaxies can separate faster than light because the underlying fabric of the cosmos expands. This distinction may sound technical, but it changes everything. It means the speed limit applies locally, within space-time, not necessarily to space-time itself. And suddenly, possibilities emerge. Could advanced civilizations somehow manipulate space-time? Could shortcuts exist? Could wormholes connect distant regions of the cosmos? Could warp drives bend geometry itself? These ideas remain speculative. No evidence confirms their feasibility. Yet remarkably, general relativity does not immediately forbid them. In fact, some solutions to Einstein's equations allow exactly such structures. The challenge lies in building them. Most would require exotic forms of matter or energy that may not exist. Still, the mathematics keeps the door slightly open. And that is one of the most beautiful aspects of science. Every answer reveals deeper questions. Every boundary hints at unexplored territory. The speed of light once seemed like a simple number, a property of illumination, a detail about how quickly sunlight travels. Today, we recognize it as something far more profound, a fundamental feature of reality itself, a limit governing causality, time, space, information, perhaps even existence. Yet despite its importance, the deeper mystery remains. Why does the universe possess this speed limit at all? Why 299,792,458 meters per second? Why not faster? Why not slower? Why does nature organize reality around this particular value? No one knows. And as our journey continues, we will encounter a possibility even stranger than faster-than-light travel. Because some physicists have begun asking whether space itself is truly fundamental, or whether it emerges from something deeper, something more abstract, something built not from matter or energy, but from information itself. And if they are correct, then the universe may be even stranger than Einstein, quantum mechanics, or science fiction ever imagined. 10. When space and time stop making sense. At the smallest scales imaginable, the universe may no longer resemble space and time at all. Imagine shrinking yourself, not to the size of an ant, not to the size of a cell, not even to the size of an atom. Keep shrinking, past molecules, past atoms, past electrons, past quarks, past everything humanity has ever directly observed. Keep going until you reach a scale so small that the very concepts of distance and duration begin to lose their meaning. A place where the familiar universe dissolves. A place where space and time themselves may no longer exist. At first, this sounds impossible. After all, space and time seem like the most fundamental ingredients of reality. Everything happens somewhere. Everything happens sometime. Every event has a location. Every process unfolds through time. Even our language assumes these concepts are universal. Try describing anything without using space or time. A tree grows in a place. A star explodes at a moment. A galaxy drifts through the cosmos. Every story depends upon both. They feel unavoidable, foundational, permanent. Yet modern physics suggests something astonishing. Space and time may not be fundamental at all. Instead, they may be emergent, a large-scale illusion, a useful approximation that breaks down when we zoom deeply enough into reality. To understand why physicists take this possibility seriously, we need to travel toward one of the smallest scales nature appears to allow, a scale known as the Planck length. This distance is unimaginably tiny, about 1.6 times 10 to the minus 35 meters. To appreciate how small that is, consider this. An atom is already incredibly small. Yet the Planck length is to an atom what an atom is to an entire galaxy. The difference is almost beyond comprehension. If a proton were enlarged to the size of the observable universe, the Planck length would still remain microscopic by comparison. This is the scale where our current theories begin to fail. And failure in science is often where the most exciting discoveries begin. Today, physics rests upon two magnificent pillars. The first is general relativity. Einstein's description of gravity, space-time, planets, stars, galaxies, and the large-scale universe. The second is quantum mechanics, the theory governing atoms, particles, fields, and the microscopic world. Both theories work extraordinarily well. Relativity predicts black holes. Quantum mechanics powers computers, lasers, and modern technology. Each has passed countless experimental tests. Yet there is a problem. When pushed to the most extreme conditions imaginable, the two theories stop cooperating. The mathematics breaks. The equations become nonsensical. Reality seems to tear itself apart. Imagine trying to build a map using two different coordinate systems. Both work perfectly in their own regions. But at the boundary, the roads no longer connect. That is roughly the situation physicists face today. At ordinary scales, relativity and quantum mechanics coexist peacefully. At the Planck scale, they collide. And when they collide, space and time themselves begin to lose their familiar meaning. One reason involves gravity. According to quantum theory, uncertainty exists everywhere. Nothing possesses perfectly definite values. Even empty space fluctuates. Tiny quantum events constantly emerge and vanish. At ordinary scales, these fluctuations are insignificant, but near the Planck length, they become enormous. The fabric of space-time itself starts fluctuating violently. Imagine looking at the surface of an ocean from high above. It appears smooth, calm, continuous. Now descend closer. Suddenly you see waves, foam, turbulence, chaotic motion. Some physicists believe space-time behaves similarly. At large scales, it appears smooth and continuous. At the smallest scales, it may resemble a storm, a turbulent quantum foam. This idea was first popularized by physicist John Wheeler. He imagined space-time becoming wildly unstable at extremely small distances. Tiny wormholes could appear and vanish. Miniature black holes might flicker into existence. The geometry of reality itself could fluctuate endlessly. In such a universe, the concept of a fixed location becomes difficult to define, because the stage itself is constantly shifting. Imagine trying to measure the position of a grain of sand while the entire beach repeatedly changes shape every fraction of a second. The notion of where becomes ambiguous. And if location becomes uncertain, what happens to time? Remarkably, time may face the same problem. For centuries, humans imagined time flowing like a river, past behind us, future ahead, a steady progression carrying events forward. Yet many equations in fundamental physics do not actually require time to exist in this familiar way. Some work perfectly well without any preferred direction. Others suggest that time may emerge from deeper processes, just as temperature emerges from the motion of countless molecules. Consider temperature. A single molecule does not possess temperature. Temperature only appears when enormous collections of particles interact. Likewise, some physicists wonder whether time itself emerges from deeper relationships among quantum systems. If true, then time is not fundamental. It is collective, an emergent phenomenon, a large-scale effect arising from something more basic. This possibility becomes even more intriguing when we examine black holes. Black holes force relativity and quantum mechanics into direct confrontation. Near their centers, densities become infinite according to classical equations. Space shrinks toward zero, time behaves strangely, the mathematics collapses. Most physicists suspect these infinities are warning signs. Nature is telling us that our theories are incomplete. A deeper framework must exist. And whatever that framework looks like, it may not contain space-time in its familiar form. This realization has inspired some of the most ambitious ideas in modern science. String theory proposes that fundamental objects are not particles at all. Instead, they are tiny, vibrating strings. Loop quantum gravity suggests that space itself may be quantized, broken into tiny, discrete units, like pixels on a screen. Other approaches imagine networks of information underlying reality, structures more abstract than geometry, more fundamental than matter, more fundamental than space itself. What is remarkable is that these wildly different theories often converge on a similar conclusion. Space and time may not sit at the foundation of reality. Something deeper lies beneath, something we have not fully uncovered. Think about that for a moment. Every memory you possess, every place you have visited, every second of your life, every sunrise, every conversation, every heartbeat, all unfold within space and time. Yet the deepest levels of existence may operate without either. Reality could be built from principles that bear little resemblance to the world we experience. And perhaps this should not surprise us. After all, our senses evolved to help us survive, not to reveal ultimate truth. A fish understands water only imperfectly. An ant does not comprehend continents. Likewise, humans may perceive only a useful approximation of reality, a simplified interface, a survival-friendly version of existence. The true foundations may be far stranger, far more abstract, far more beautiful. And this brings us to a profound possibility. If space and time emerge from something deeper, what exactly is that deeper layer? What remains when geometry disappears? What survives when location and duration lose meaning? As we continue our journey, we will explore one of the boldest ideas in modern physics, an idea suggesting that beneath matter, beneath energy, beneath space, and beneath time, the universe may ultimately be built from information itself. And if that idea is correct, reality may be far more like a cosmic language than a physical machine. 11. The possibility that reality is information. Some physicists suspect that information, not matter, may be the true foundation of existence. Imagine for a moment that everything you have ever touched is an illusion. Not an illusion in the sense that it is fake, not an illusion like a dream, but an illusion in the sense that what you perceive is not what truly exists at the deepest level. The chair beneath you feels solid. The walls around you seem real. Your body appears to be made of matter, atoms, molecules, cells, organs, a collection of physical objects occupying physical space. That picture feels obvious. It feels undeniable. Yet throughout our journey, that certainty has been slowly eroding. First, we discovered that atoms are mostly empty space. Then, quantum mechanics revealed that particles often behave less like objects and more like probabilities. Entanglement suggested that distant parts of reality can remain connected in ways that ignore our intuitive understanding of separation. And finally, we arrived at a place where space and time themselves may not be fundamental. If all of those discoveries are true, a profound question emerges. What is left? If matter is not truly solid, if space and time are not fundamental, what exactly is reality made of? Some physicists believe the answer may be information. Not particles, not energy, not matter. Information. At first, that sounds absurd. Information feels like something humans invented. Books contain information. Computers process information. Libraries store information. Surely information cannot be more fundamental than physical reality itself. After all, don't you need matter first before information can exist? Surprisingly, modern physics has begun challenging that assumption. One of the first clues emerged from an unexpected place: black holes. For much of the 20th century, black holes were viewed as cosmic garbage disposals. Anything falling inside disappeared forever. Matter vanished. Information vanished. Everything was lost beyond the event horizon. Simple, or so it seemed. Then physicists started asking uncomfortable questions. According to quantum mechanics, information cannot simply disappear. The laws governing the microscopic universe are reversible. Information should always be preserved, yet black holes appeared to destroy it. The contradiction became known as the black hole information paradox, and it triggered one of the biggest debates in modern physics. For decades, some of the world's greatest minds struggled with the problem. Among them was physicist Stephen Hawking. Initially, Hawking argued that black holes destroy information forever. Many others disagreed. The argument became legendary, because if information could truly be destroyed, quantum mechanics itself might be incomplete. Eventually, after years of debate, evidence increasingly pointed toward a remarkable conclusion. Information survives, somehow, even inside black holes. Exactly how remains an active area of research, but the implications were enormous. Because suddenly information was no longer just a useful concept. It appeared to be protected by the deepest laws of nature, almost as if reality cared about information itself. And then things became even stranger. In the 1990s, physicists Gerard 't Hooft and Leonard Susskind developed an extraordinary idea. An idea so radical that it initially sounded like science fiction. They proposed something called the holographic principle. To understand it, imagine a hologram. A holographic image appears three-dimensional. It possesses depth, structure, volume. Yet all of that information is actually encoded on a two-dimensional surface. The three-dimensional appearance emerges from a lower dimensional reality. Now imagine applying that concept to the entire universe. What if our three-dimensional world works similarly? What if the information describing everything inside a region of space is actually stored on its boundary? In other words, what if reality itself is a cosmic hologram? At first glance, the idea sounds outrageous. Yet astonishingly, the mathematics keeps working, again and again, in multiple areas of theoretical physics. The holographic principle has become one of the most influential ideas in modern attempts to understand gravity and quantum mechanics. No one knows whether it represents ultimate truth, but it continues appearing in places where deep insights emerge, and it points toward a remarkable possibility. The universe may not fundamentally consist of objects. It may fundamentally consist of information. Think about your favorite photograph. At first glance, it contains people, mountains, clouds, colors, memories. But inside a computer, none of those things exist directly. There are only patterns of information, bits, encoded relationships. The image emerges from the information. Some physicists wonder whether reality itself behaves similarly. Perhaps matter emerges from information. Perhaps particles emerge from information. Perhaps space-time emerges from information. The universe becomes less like a machine and more like a process, a vast informational structure generating everything we experience. This idea gained even more attention through the work of physicist John Wheeler. Wheeler proposed a famous phrase, "it from bit." The phrase sounds simple, but its implications are enormous. It refers to physical reality, matter, energy, particles, objects, everything. Bit refers to information. According to Wheeler's vision, every physical thing ultimately arises from informational distinctions, answers to questions, yes or no, 1 or 0. The physical universe emerges from the logic of information itself. Today, researchers continue exploring variations of this concept. Quantum information theory has become one of the most active fields in physics. Increasingly, scientists find that information sits at the center of many fundamental mysteries. Black holes, quantum entanglement, space-time geometry, the foundations of quantum mechanics. Again and again, information appears, like a hidden thread connecting seemingly unrelated phenomena. And perhaps the most surprising realization is this: information does not necessarily require matter, but matter may require information. Consider a book. The paper is not the story. The ink is not the story. The story exists in the arrangement, the relationships, the information encoded within the physical medium. Likewise, some physicists suspect that particles are not the deepest layer of reality. Particles may simply be manifestations of deeper informational structures, patterns appearing within a more fundamental system, the way waves appear on an ocean, or whirlpools emerge within flowing water. The pattern feels real because it is real, but it is not the deepest level. Beneath it lies something more fundamental. And if that idea is correct, then one of humanity's oldest assumptions may need revision. For centuries, we believed reality was made of stuff, matter, substance, objects. But perhaps reality is made of relationships instead. Information, connections, patterns. The universe becomes less like a collection of things and more like a language, a cosmic code unfolding across unimaginable scales. Of course, many questions remain unanswered. What exactly is information? Where does it come from? Why does it exist? Can information itself emerge from something deeper? No one knows. And that uncertainty is what makes this frontier so fascinating. Because the deeper we descend into reality, the less reality resembles our everyday experience. The familiar world slowly dissolves. Matter becomes energy. Energy becomes quantum fields. Fields become information. And beyond information, there may be something deeper still. Something so strange that even our best theories struggle to describe it. As we continue our journey, we will encounter an idea that pushes the limits of imagination itself. An idea suggesting that reality may not merely contain observers. Reality may require them. And if that possibility contains even a fragment of truth, the relationship between consciousness and the universe may be far more profound than anyone once imagined. 12. Could the universe be a giant computation? What if reality behaves less like a machine and more like an unimaginably vast process of computation? For hundreds of years, humanity has compared the universe to a machine. It was an understandable analogy. Machines were among the most sophisticated creations people had ever seen. Clocks, engines, factories, complex systems made from countless interacting parts. The universe seemed similar. Planets orbited stars. Stars orbited galaxies. Everything followed predictable laws. The cosmos looked like an enormous clockwork mechanism, a machine operating according to mathematical rules. But over the last century, something strange happened. The deeper physicists explored reality, the less the machine analogy seemed to fit. Quantum mechanics revealed probabilities instead of certainty. Relativity merged space and time into a dynamic geometry. Information emerged as a fundamental ingredient in black holes and quantum theory. And increasingly, scientists began asking a radical question. What if the universe is not primarily a machine? What if it behaves more like a computation? At first, this sounds like a subtle distinction. Machines compute things. Computers are machines. What's the difference? The difference is deeper than it first appears. A machine is made of physical components: gears, levers, springs, metal parts interacting mechanically. A computation is something more abstract. A computation is a process, a transformation of information. The same computation can run on silicon chips, mechanical gears, quantum processors, or even biological neurons. The physical substrate changes, the informational process remains. And that raises an extraordinary possibility. Perhaps what truly matters is not the material from which reality is built. Perhaps what matters is the information being processed. Imagine opening a video game. You see mountains, rivers, cities, characters, entire worlds. To the player, these objects feel real within the game. Yet beneath the images lies something very different. Not mountains, not rivers, not people. Only information. Mathematical rules, computational processes generating the experience. No one inside the game sees the code directly. They experience the world the code creates. Now pause for a moment. What if reality works in a somewhat similar way? Not necessarily as a literal computer simulation. That is a separate idea. But as a system where informational processes generate the physical universe we observe. Increasingly, some physicists believe this possibility deserves serious consideration. One reason comes from an unexpected source: the laws of physics themselves. When scientists describe reality mathematically, they often discover that physical systems behave remarkably like information processing systems. Particles interact according to rules. Quantum states evolve according to rules. Information flows through physical systems according to rules. The universe seems astonishingly good at computation. In fact, physicist Seth Lloyd once proposed a fascinating idea. If every physical interaction can be viewed as a form of information processing, then the universe itself may be performing computations continuously. Every collision between particles, every chemical reaction, every fusion event inside stars, every interaction throughout cosmic history. All of it can be viewed as information evolving according to physical laws. The universe becomes less like a collection of objects and more like an ongoing calculation, a process unfolding across billions of years. Of course, this immediately raises a profound question. If the universe is computing something, what is it computing? The simplest answer may be surprising. It is computing itself. Reality continuously updates its own state. Every moment emerges from the previous moment. The universe processes information and generates the next version of itself. In this picture, existence is not static. Reality is an active process, a computation without an external operator, a calculation running since the Big Bang, perhaps even before. And remarkably, some of the deepest mysteries in physics begin looking different when viewed through this lens. Consider quantum mechanics. For decades, physicists have struggled to understand why quantum systems behave probabilistically. Why does nature appear to evaluate multiple possibilities before producing an outcome? Why do wave functions contain vast landscapes of potential realities? Some researchers speculate that these features resemble information processing. The universe explores possibilities, updates probabilities, generates outcomes, not unlike certain computational systems. Again, these ideas remain speculative, but they continue attracting attention because they offer new ways to think about old mysteries. And nowhere is this more evident than in the relationship between information and entropy. Entropy is often described as disorder, but many physicists prefer another interpretation. Entropy measures missing information, the number of possible ways a system can be arranged. Viewed this way, thermodynamics becomes deeply connected to information theory. Heat, order, disorder, complexity, all become informational concepts. Suddenly, information is not merely a tool for describing reality. It becomes woven into the fabric of physical law itself. Then there is the astonishing connection between computation and black holes. In recent decades, physicists discovered that black holes possess entropy. They store information. In fact, the amount of information a black hole can contain appears directly related to the surface area of its event horizon, not its volume, its surface. This surprising relationship became one of the foundations of the holographic principle we discussed earlier. And once again, information emerged as something fundamental, almost as if the universe keeps whispering the same message. Look deeper. Information matters. Look deeper still. Information may be everything. But perhaps the most intriguing question concerns consciousness itself. After all, you are not merely observing information, you are processing it. Your brain constantly receives signals from the world. Photons strike your eyes, sound waves vibrate your ears, neurons exchange electrical patterns. Information flows endlessly through your nervous system, and somehow from that informational activity, subjective experience emerges. Awareness appears, thoughts appear, a conscious observer appears. No one fully understands how. This remains one of the greatest mysteries in science. Yet the connection is impossible to ignore. Information sits at the center of both modern physics and conscious experience. Some researchers wonder whether this overlap is significant, whether information represents a bridge between physical reality and awareness, whether consciousness itself emerges from certain informational structures. At present, nobody knows, but the possibility remains fascinating. Because if reality is fundamentally informational, then consciousness may not be as disconnected from the universe as we often assume. We may be part of the same informational process, patterns arising within larger patterns, observers emerging inside a cosmic computation. And suddenly, the ancient human desire to understand existence acquires a new dimension. The universe becomes something extraordinary, not merely a collection of stars and galaxies, not merely matter drifting through empty space, but a vast process unfolding across cosmic time, a process capable of generating atoms, planets, life, consciousness, and eventually beings capable of asking questions about the process itself. In a strange sense, the universe may be computing observers, capable of understanding the computation. Reality becomes self-referential, a cosmic feedback loop, the universe learning about itself through the minds it creates. Of course, enormous mysteries remain. Who or what established the rules? Why do these particular laws exist? Why does information exist at all? And perhaps most importantly, can a computation explain everything? Or does something even deeper lie beneath? Because as radical as the computational view appears, it may not be the final layer. Some physicists suspect an even stranger possibility, one that challenges our deepest assumptions about existence itself. A possibility suggesting that reality may not merely process information. Reality may emerge from relationships between observers and information. And if that idea is correct, then the boundary between the universe and consciousness may be far less clear than anyone once imagined. Tell me below, do you think reality is fundamentally physical or fundamentally informational? And as we continue our journey deeper into the foundations of existence, prepare for one of the most unsettling possibilities yet. The observer may not be separate from reality at all. 13. The mystery of consciousness. The mystery of consciousness. The most complex object we know may be the thing reading these words right now. Take a moment and consider something extraordinary. Not the stars above you, not black holes, not distant galaxies, not the age of the universe. Instead, consider the object that is currently experiencing this sentence, your mind. The fact that you are aware right now may be one of the greatest mysteries in existence. In some ways, consciousness is so familiar that we rarely stop to think about it. You wake up, you see colors, you hear sounds, you feel emotions, you experience memories. You possess an inner world, a private universe that exists nowhere else. And because this experience accompanies every moment of your life, it feels natural, obvious, almost trivial. But when scientists attempt to explain it, something remarkable happens. The mystery becomes enormous. Because while we understand many things about the brain, we still do not understand why consciousness exists at all. We know that neurons fire. We know that electrical signals travel through vast networks. We know that chemicals influence thoughts, emotions, and memories. Modern neuroscience has mapped countless aspects of brain activity, yet a profound question remains unanswered. Why should any of that activity produce experience? Imagine examining a computer. You can trace electrical currents through its circuits. You can monitor information flowing between processors. You can predict outputs from inputs. But nowhere inside the machine do you find an experience. Nowhere do you find a sensation of redness, or sadness, or joy, or curiosity. The machine processes information, but does it feel anything? As far as we know, it does not. Yet your brain is also processing information. Billions of neurons exchanging signals every second. Electrochemical activity unfolding continuously. And somehow, from that physical activity, awareness emerges. The lights come on. A subjective universe appears. The philosopher David Chalmers famously called this the hard problem of consciousness. Not because consciousness is difficult to study, but because explaining experience itself seems fundamentally different from explaining behavior. Imagine two questions. The first asks, how does the brain recognize faces? Science can answer that. How does memory work? Science can investigate that too. How does vision process light? Again, neuroscience provides explanations. These are difficult problems, but they appear solvable. The second question is stranger. Why does seeing a sunset feel like something? Why is there an experience associated with perception? Why is there an inner observer at all? That question remains deeply mysterious, and some scientists believe it may force us to rethink reality itself. Because the deeper researchers investigate consciousness, the more unusual the problem becomes. Consider this. Everything you have ever known about the universe exists inside your conscious experience. Stars, galaxies, black holes, physics, mathematics, history, even the concept of an external world. All of it appears within awareness. This does not mean the external world is imaginary, but it does highlight something important. Consciousness is not merely another object inside reality. It is the medium through which reality is encountered. Without consciousness, there is no experience of a universe. There may still be a universe, but there is no one there to know it. This realization has fascinated philosophers and scientists for centuries, and it has led to some surprisingly radical ideas. One possibility is that consciousness emerges entirely from physical processes. In this view, awareness is a product of sufficiently complex brains. Nothing mystical is required. No special ingredient exists beyond matter and energy. Eventually, science will explain exactly how neurons generate subjective experience. Many neuroscientists favor this perspective, and it may ultimately prove correct. But there are challenges, because despite decades of research, nobody has identified precisely how physical activity becomes conscious experience. The gap remains, and some researchers wonder whether consciousness might be more fundamental than we assume. This leads us toward a controversial idea known as panpsychism. The name sounds exotic, but the basic concept is surprisingly simple. Instead of consciousness emerging suddenly in complex brains, perhaps some extremely primitive form of experience exists throughout nature. Not human consciousness, not thoughts, not emotions. Just tiny building blocks of subjective experience. According to this view, consciousness may be as fundamental as space, time, or mass. A basic ingredient of reality. The idea remains highly debated. Many scientists reject it. Others find it increasingly intriguing, because it offers a way to bridge the enormous gap between matter and awareness. Whether it is correct remains unknown, but it illustrates how seriously some thinkers are taking the mystery. Then there is another possibility, one even stranger. What if consciousness and information are deeply connected? In our previous chapter, we explored the possibility that reality may be fundamentally informational. Some theories of consciousness point in a similar direction. One influential example is integrated information theory. According to this framework, consciousness arises when information becomes integrated in specific ways. The more unified and interconnected a system's information structure becomes, the greater its level of consciousness may be. The theory remains controversial, yet it highlights an increasingly important trend. Information keeps appearing. In quantum mechanics, in black holes, in space-time, and now, potentially, in consciousness itself. It is as if multiple scientific mysteries are converging toward a common foundation. Of course, consciousness becomes even more intriguing when we consider quantum mechanics. Over the years, some researchers have speculated that quantum phenomena may play a role in awareness. Perhaps quantum processes inside the brain contribute to conscious experience. Perhaps observation itself has deeper connections to reality than we currently understand. Most of these ideas remain speculative. Evidence is limited. Many neuroscientists remain skeptical. Yet the questions persist because the mystery remains unresolved. And unresolved mysteries attract bold ideas. But perhaps the most astonishing fact is not that consciousness exists. It is that consciousness evolved. Somehow, over billions of years, a universe composed of particles and fields produced stars. Stars forged heavy elements. Those elements formed planets. Life emerged. Evolution unfolded. Brains developed. And eventually, somewhere on a small rocky world orbiting an ordinary star, the universe became capable of asking questions about itself. Think about that. For nearly 14 billion years, the cosmos expanded in silence. Galaxies formed, stars exploded, planets drifted through darkness. Then consciousness appeared. And for the first time, the universe gained witnesses, observers, storytellers, question askers. You. In a very real sense, every conscious being represents something extraordinary. A region of the universe becoming aware of the universe. Atoms contemplating atoms, stardust investigating stardust, reality looking into a mirror. Perhaps that is why consciousness feels so profound, because it occupies a unique position in existence. It is both part of the universe and a window through which the universe experiences itself. And yet, the mystery remains. What exactly is awareness? Why does it exist? How does subjective experience emerge? Can science fully explain it? Or will consciousness ultimately require a deeper understanding of reality itself? No one knows. And perhaps that uncertainty is fitting, because after all our explorations, from quantum fields to space-time, from black holes to information, we have arrived at a mystery that is closer than anything else we have encountered. Closer than the stars, closer than your own heartbeat. The mystery of the observer, the mystery of the self. And as we continue our journey, we will confront an idea that may be even more unsettling. Because if consciousness plays a deeper role in reality than we currently understand, then the universe we experience may not simply be observed. It may be participating in the act of observation itself. And that possibility leads us directly toward one of the strangest questions modern science has ever dared to ask. Could reality be far stranger than even consciousness allows us to imagine? 14. Why science still cannot explain awareness. Despite centuries of progress, nobody truly understands why subjective experience exists. Imagine that tomorrow morning, scientists announce something extraordinary. They have created a complete map of your brain. Every neuron, every connection, every electrical signal, every chemical reaction. Nothing is missing. The map is perfect, so detailed that it predicts every decision you will make for the rest of your life. Every memory, every emotion, every dream, every fear, every moment of joy, everything. Now imagine asking a simple question. Where inside that map is the experience of being you? Where is the feeling of seeing the color blue? Where is the sensation of warmth from sunlight? Where is the feeling of nostalgia when an old song begins playing? Where is the experience itself? The uncomfortable answer is that nobody knows. And that is precisely why consciousness remains one of the deepest mysteries in science. Because despite centuries of progress, we still cannot explain the most obvious thing any human being has ever encountered: the fact that experience exists at all. Think about how strange that is. Humanity has measured the age of the universe. We have detected gravitational waves produced by colliding black holes billions of light years away. We have mapped the cosmic microwave background. We have split atoms, decoded DNA, photographed black holes, sent spacecraft beyond the planets. And yet the thing each of us experiences every second of every day remains fundamentally unexplained. In some ways, awareness is more mysterious than dark matter, more mysterious than black holes, more mysterious than the Big Bang, because all of those mysteries exist within consciousness. Without awareness, there is no mystery to investigate, no universe to observe, no question to ask. And that is where the problem becomes deeply unsettling. Because science is exceptionally good at explaining behavior. It can tell us how neurons communicate, how memories form, how visual information travels from the eye to the brain, how emotions correlate with neurotransmitters, how sleep affects cognition, how damage to certain brain regions changes personality. The progress has been extraordinary. But notice something important. These explanations describe mechanisms. They explain what the brain does. They do not explain why those processes feel like something from the inside. Imagine a robot. A sufficiently advanced machine could recognize faces, understand language, respond emotionally, write poetry, perhaps even claim to be conscious. From the outside, its behavior might be indistinguishable from a human being. But would it actually experience anything? Would there be an inner world? Would there be a feeling of existence? Or would it simply process information without awareness? Nobody knows. And that uncertainty reveals something profound. Behavior and consciousness are not necessarily the same thing. You can explain behavior mechanically. Awareness seems to demand something more. Philosophers sometimes illustrate this with a thought experiment known as the philosophical zombie. Imagine a person who looks exactly like a human, talks exactly like a human, laughs, cries, falls in love, writes books, explains quantum physics, argues about philosophy. From the outside, there is no difference whatsoever. Yet internally, there is no experience, no awareness, no consciousness, only behavior. The zombie acts conscious without actually being conscious. The disturbing part is this: how would anyone know the difference? From the outside, you couldn't, and that reveals the central difficulty. Consciousness is private. Entirely private. You can observe someone else's behavior, you can scan their brain, you can analyze their neural activity, but you can never directly access their experience. The only consciousness you know with absolute certainty is your own. Everything else is inferred. This makes consciousness uniquely difficult to study. Most scientific phenomena are publicly observable. Gravity affects everyone. Light behaves consistently. Atoms can be measured. Galaxies can be photographed. But awareness exists from a first-person perspective. Science traditionally operates from a third-person perspective. And somewhere between those viewpoints lies a gap that nobody has successfully bridged. This gap has inspired countless theories. Some researchers believe consciousness emerges naturally once information becomes sufficiently complex. Others suspect the brain functions as a special kind of biological information processing system. Still others argue that entirely new principles may be required. But no theory has achieved universal acceptance. No theory has solved the mystery completely. And perhaps the strangest part is that consciousness seems impossible to ignore. Every attempt to explain reality eventually encounters it. Physics explains matter, but who observes the matter? Neuroscience explains brains, but who experiences the brain? Information theory explains data, but who becomes aware of the information? Again and again, consciousness appears, waiting at the end of the chain, like a question reality keeps asking us. Some thinkers have gone even further. They argue that perhaps consciousness is not a product of the universe. Perhaps consciousness is a fundamental feature of the universe. This idea sounds radical, yet remember how many times science has encountered similar surprises. Once, space seemed fundamental. Now it may emerge from something deeper. Once, matter seemed fundamental. Now information may lie beneath it. Once, time appeared absolute. Now it may be emergent. Why should consciousness be different? Of course, this does not mean rocks are conscious, or that stars have thoughts. The possibilities are far more subtle. Perhaps awareness exists as a basic property that becomes increasingly organized in complex systems. Much like gravity exists everywhere, but becomes noticeable only around massive objects. The idea remains controversial. Many scientists reject it. Others find it increasingly difficult to dismiss. Because despite decades of research, consciousness refuses to fit neatly into existing categories. And then there is another mystery, one that makes the problem even stranger. Why does consciousness possess the particular qualities it does? Why does red look red? Why does music feel emotional? Why does pain hurt? Why do experiences have texture? Scientists call these qualities qualia, the raw subjective qualities of experience, and they present a challenge unlike anything else in science. A brain scan can reveal which neurons activate when you see a sunset, but it cannot explain why the sunset feels beautiful. It can measure activity associated with happiness, but it cannot capture the experience of happiness itself. There seems to be an explanatory gap, a missing bridge between physical processes and subjective experience. Some researchers believe that bridge will eventually be found. Others suspect the gap may force a revolutionary shift in our understanding of reality. After all, history repeatedly teaches the same lesson. When a mystery survives long enough, it often reveals that our assumptions were incomplete. The Earth was not the center of the cosmos. Space and time were not absolute. Matter was not solid. Perhaps consciousness is pointing toward another revolution, one we have not yet fully imagined. And if that is true, then awareness may be more than a curious byproduct of evolution. It may hold clues about the deepest structure of existence itself. Because after all our explorations, from atoms to galaxies, from quantum fields to information, the greatest mystery remains astonishingly close. Closer than the stars, closer than your heartbeat, closer than your thoughts. The mystery is the fact that there is something experiencing those thoughts at all. And as we continue our journey, we arrive at an even more unsettling possibility. What if consciousness is not merely observing reality? What if reality, at its deepest level, somehow depends upon observers existing in the first place? That question leads us directly toward one of the most controversial and fascinating ideas ever inspired by modern physics. The possibility that the universe and the observer may be far more deeply connected than either can exist alone. 15. The observer may be the greatest cosmic mystery. The deepest puzzle in the universe may not be black holes, dark matter, or the Big Bang, but consciousness itself. For most of human history, we assumed the universe was the mystery. The stars were mysterious, the planets were mysterious, lightning was mysterious, gravity was mysterious, the origin of the cosmos was mysterious. And over time, science began solving those mysteries, one by one. The Earth was no longer the center of creation. The planets became worlds, the stars became suns, galaxies replaced the small universe our ancestors once imagined. The cosmos grew larger, older, stranger. And yet something unexpected happened. The deeper we looked outward, the more we were forced to look inward. Because every discovery encountered the same unavoidable fact. There must be an observer. Someone has to witness the stars. Someone has to formulate the equations. Someone has to ask the questions. And suddenly, after centuries spent studying the universe, humanity found itself confronting something perhaps even more mysterious. The observer itself. You. Not your body, not your brain, not the electrical signals moving through neurons, but the fact that there is an experience happening at all. The fact that there is a perspective, a point of view, a conscious awareness witnessing reality unfold. This may sound familiar by now. After all, we have spent the last 2 chapters discussing consciousness. But here the mystery becomes even deeper. Because consciousness is not merely difficult to explain, it may occupy a unique position within our understanding of reality. Consider this. Every scientific measurement ever performed required an observation. Every experiment, every telescope image, every particle collision, every mathematical model tested against nature. At some stage, information had to become part of an observer's experience. Science depends upon observation. Yet observation itself remains poorly understood, and nowhere does this become more fascinating than in quantum mechanics. For nearly a century, physicists have wrestled with one of the strangest features of the quantum world. Before measurement, quantum systems often exist in superpositions. Multiple possible outcomes coexist mathematically. Then, a measurement occurs. A specific outcome appears. The wave function seems to collapse, and reality becomes definite. Exactly what causes this transition remains one of the most debated questions in science. Different interpretations offer different answers. Some propose that interaction with the environment causes the collapse. Others suggest that all possibilities continue existing in parallel branches of reality. Still others explore more exotic explanations. But throughout the history of these debates, one idea repeatedly emerges. What role does the observer play? Now it is important to be careful here. Popular culture often exaggerates these ideas. Quantum mechanics does not prove that human thoughts create reality. It does not demonstrate magical powers. It does not show that consciousness controls the universe. The science is far more subtle than that. Yet the observer continues appearing in places where physicists least expected it. And that alone is remarkable. Because traditionally, science aimed to remove the observer from the picture. The ideal scientific description is objective, independent of perspective, independent of human experience. Reality should exist whether anyone observes it or not, and almost certainly it does. The universe existed billions of years before conscious life emerged. Stars formed, galaxies evolved, planets orbited, all without human observers. Yet when we attempt to describe reality at its deepest levels, the observer keeps returning, like a character who refuses to leave the story. Perhaps the reason is simple. Perhaps consciousness is merely another natural phenomenon waiting to be explained. Or perhaps something deeper is happening. Perhaps the observer occupies a more fundamental role than we currently understand. This possibility has fascinated some of the greatest thinkers in science. Among them was physicist John Wheeler. Wheeler proposed a provocative idea known as the participatory universe. His suggestion was not that humans create reality. Rather, he wondered whether observers and reality might be deeply interconnected, whether the act of observation plays a more significant role in existence than classical physics assumed. One of Wheeler's most famous thought experiments involved imagining the entire universe as a self-excited circuit, a loop. The universe produces observers. Observers study the universe, and through observation, the universe becomes known. Reality and awareness become part of the same ongoing process. At first glance, this sounds philosophical, almost poetic, but it reflects a profound question. Can a universe truly be described without observers? Or is observation itself part of the structure being described? The more we think about it, the stranger the question becomes. Imagine a universe completely devoid of consciousness. No life, no minds, no awareness, no experiences. Stars still shine, galaxies still collide, black holes still consume matter, physics still unfolds, but there is nobody there to know it, nobody to witness the beauty, nobody to ask questions, nobody to construct meaning. In one sense, the universe exists. In another sense, the concept of existence becomes difficult to discuss, because every statement about reality ultimately arises within awareness. This realization has led some philosophers to suggest that consciousness may be the most immediate fact we know. Before atoms, before galaxies, before space-time, there is experience. Not because consciousness creates those things, but because consciousness is the medium through which they are encountered. You never experience reality directly. You experience perceptions, sensations, thoughts. images generated by your nervous system. Everything you know about the cosmos arrives through awareness. And that makes consciousness uniquely important. Not necessarily because it is fundamental to physics, but because it is fundamental to knowledge itself. Yet the mystery deepens even further, because consciousness appears astonishingly rare. As far as we currently know, the observable universe contains hundreds of billions of galaxies. Each galaxy contains hundreds of billions of stars. The total number of planets may exceed the number of grains of sand on Earth. And yet, despite this unimaginable abundance, we have not found confirmed evidence of another conscious civilization. Not yet. Perhaps life is common. Perhaps intelligence emerges everywhere. Perhaps the cosmos teems with observers. Or perhaps awareness is extraordinarily rare, a fragile phenomenon emerging only under special circumstances. If that is true, consciousness becomes even more extraordinary. The universe spent billions of years producing stars, forging heavy elements, building planets, evolving life, only to generate something capable of reflecting upon existence itself. The observer may represent one of the rarest outcomes in cosmic history, and perhaps one of the most precious. Because consciousness allows something remarkable to occur, the universe becomes aware of its own existence. Think about that carefully. The atoms in your body were forged inside ancient stars. Those stars formed from matter created shortly after the Big Bang. Every particle within you has traveled through cosmic history for billions of years. And now, assembled into a conscious mind, those particles can contemplate their own origins. The universe has developed the ability to ask where it came from, why it exists, what reality is, whether meaning exists, whether other observers exist. This is not merely intelligence. It is self-reflection on a cosmic scale. Perhaps that is why the observer feels so mysterious, because consciousness stands at the intersection of two great unknowns, the mystery of reality and the mystery of awareness. We understand neither completely, and yet they appear inseparable. Reality produces observers. Observers investigate reality. The cycle continues, a cosmic loop stretching across billions of years. And as our journey approaches its conclusion, one final question remains. A question even deeper than consciousness, even deeper than information, even deeper than space-time itself. Because after everything we have explored, we still have not answered the ultimate mystery. Why does anything exist at all? Why is there a universe instead of nothing? Why are there laws of physics? Why is there awareness capable of asking these questions? Why is there something rather than nothing? And that question will guide us into the final chapter of our journey through the deepest mysteries of existence. 16. The day reality starts to break. The closer science gets to the foundations of existence, the stranger reality becomes. Imagine standing at the edge of a map. Not a map of Earth, not a map of the solar system, not even a map of the observable universe. Imagine standing at the edge of human understanding itself. Beyond this point, the familiar landmarks begin to disappear. Matter becomes uncertain, space becomes flexible, time becomes questionable. And reality itself begins to feel less like a place and more like a mystery. For centuries, science has been one of humanity's greatest success stories. Each generation pushed the frontier a little farther. The ancient world gave way to astronomy. Astronomy gave way to physics. Physics revealed atoms. Atoms revealed particles. Particles revealed quantum fields. Every discovery seemed to bring us closer to the ultimate foundation of existence, closer to the bedrock beneath reality, closer to the final answer. And yet something unexpected happened. The deeper we looked, the less solid that foundation appeared. Instead of certainty, we found questions. Instead of simplicity, we found complexity. Instead of final answers, we discovered deeper mysteries. It is almost as though reality retreats whenever we approach it, like a horizon that continually moves farther away. Think about the journey we have taken. At first, the universe appeared straightforward, a collection of objects moving through space, planets orbiting stars, stars orbiting galaxies, a giant cosmic machine operating according to elegant laws. But then atoms entered the picture, and suddenly matter stopped being solid. The objects we trusted most turned out to consist mostly of empty space. The certainty began to crack. Then quantum mechanics arrived. Particles became probabilities. Certainty became uncertainty. Objects became wave functions. Reality stopped behaving like common sense. The cracks widened. Next came relativity. Space and time merged into a single fabric. Gravity became geometry. The stage upon which existence unfolds became part of the story itself. The cracks spread further. Then black holes appeared, regions where space-time bends so dramatically that our equations begin to fail. Places where information, gravity, and quantum mechanics collide. Places where our best theories stop speaking the same language. And suddenly the cracks became impossible to ignore. As scientists pushed deeper, something remarkable emerged. Reality seemed less like matter and more like information. Less like objects and more like relationships. Less like things and more like processes. The universe began transforming from a machine into something far stranger, a vast network of interactions, patterns emerging from deeper patterns, structures emerging from hidden structures. And yet even information failed to solve every mystery. Because consciousness remained, the observer remained. The fact that there is an experience happening right now remained. And somehow, after everything else dissolved, awareness continued staring back at us, waiting, unexplained, unresolved. Perhaps that is why modern physics often feels so different from the science many people imagine. Popular culture tends to portray science as a collection of answers, a machine for turning mysteries into facts. But at the deepest levels, science often does the opposite. It reveals how little we truly understand. Every major breakthrough opens entirely new realms of uncertainty. Every solved mystery exposes larger mysteries beyond it. The closer we approach the foundations of reality, the stranger reality becomes. Consider one of the most unsettling possibilities. What if there is no final layer? What if reality is not a pyramid with a foundation waiting at the bottom? What if every answer reveals another question beneath it? Imagine peeling an onion. Layer after layer comes away. You expect to reach the center. But what if there is no center? What if the process continues forever? Some philosophers and physicists have seriously entertained this possibility. Perhaps reality is infinitely deep. Perhaps there is no ultimate explanation, no final equation, no last piece of the puzzle. Only increasingly profound levels of understanding, each revealing another horizon beyond. At first, this idea feels frustrating. Humans crave closure. We want definitive answers. We want certainty. We want the universe to make sense. Yet perhaps the absence of final answers is not a flaw. Perhaps it is part of what makes reality so extraordinary. After all, a mystery completely solved ceases to be a mystery. Wonder survives because questions remain. And there may be no greater source of wonder than existence itself. Why is there something rather than nothing? We still do not know. Why do the laws of physics exist? We still do not know. Why does consciousness exist? We still do not know. Why does mathematics describe reality so effectively? We still do not know. Why does the universe permit complexity, life, and awareness? We still do not know. And perhaps most astonishingly, why is the universe comprehensible at all? Why should a collection of atoms on a small planet around an ordinary star be capable of understanding black holes, quantum fields, and cosmic history? Why should reality allow itself to be understood? No one knows. Yet here we are, a species that emerged only moments ago on the cosmic timescale, looking outward, looking inward, trying to decipher a universe nearly 14 billion years old. And despite all our limitations, we have learned remarkable things. We have measured the age of the cosmos, mapped distant galaxies, observed the remnants of the Big Bang, detected ripples in space-time, photographed black holes, decoded the chemistry of stars, discovered planets around distant suns. all while carrying brains that evolved primarily to find food, avoid predators, and survive long enough to reproduce. That alone feels miraculous. Perhaps even more miraculous is the fact that the universe produced beings capable of asking these questions in the first place. Because for most of cosmic history, there were no observers, no questions, no curiosity. Only stars burning in silence, galaxies drifting through darkness. Then awareness appeared, and with awareness came wonder. The universe gained witnesses. Storytellers, dreamers, scientists, philosophers. People lying awake at night, staring into the darkness and asking impossible questions. People like you. In some sense, that may be the most extraordinary fact of all. Not that the universe is vast, not that black holes exist, not that quantum mechanics is strange, but that a small portion of the cosmos became capable of contemplating the whole. That matter became curious about itself. That stardust learned to wonder. And perhaps that is where our journey ultimately leads. Not toward certainty, not toward final answers, but toward a deeper appreciation of the mystery. Because the universe is not merely a collection of facts waiting to be discovered. It is an unfolding story. A story that began long before Earth existed. A story that will continue long after humanity is gone. A story that we are fortunate enough to witness for a brief moment. And perhaps the greatest lesson hidden within all these mysteries is this. The goal is not necessarily to solve every question. The goal is to keep asking them, to remain curious, to remain amazed, to continue exploring, even when the answers become strange, especially when they become strange. Because every mystery we have explored tonight points toward the same realization. Reality is deeper than it first appears, stranger than it first appears, more beautiful than it first appears. And no matter how far science advances, there may always be horizons beyond the horizon. Unknown territories waiting to be discovered, new mysteries waiting to emerge, new questions waiting to be asked. As you drift toward sleep tonight, remember that the universe is not only stranger than we once imagined, it may be stranger than we are capable of imagining. Yet for a brief moment in cosmic history, you have the privilege of wondering about it. You are part of a universe that became conscious enough to question its own existence. A universe that learned to look back at itself through your eyes. Sleep well, and I'll see you on our next journey into the unknown.